Alrighty. So coming to the steps of fine tuning, back to that. So first is the forward pass. So you gather the data, you divided the whole data into three data sets, three pools called as the training, validation, and test. And then you start with the forward pass. In forward pass, what you do is suppose let's take an example of an item price predictor, right? Wherein you give the descriptions about the item, and your model has to predict the price for that. You're fine tuning the model on those lines, right? And suppose you use some Hugging Face data sets and pulled out an Amazon data set from that and use that for your training. Okay. All right. So you have the inputs, you have your price also, which you have already scraped from the Amazon. Now you give the query about the items, saying, I want the price of this item, and these are the details of the item. Okay. Give that query to your model in the forward pass, and your model predicts the price for that. Okay. And you have the actual price of the from the website as well. Okay. The ground truth, which we call it here. And the one that model predicts is the prediction, is what we call it, right? Now in forward pass, what happens deeply is when you query the model, right, instead of giving a single price as the output, your model outputs a probability distribution. Suppose it predicts 10 prices of the item, and each of them, they have their own probabilities, and so they all will add up to one, right? Now you got, say, $99 as having the probability of 0.3, which may be the highest, suppose, amongst the 10 items predicted. And you your model outputted, you picked up that price, the model, the prediction with the highest probability as the output of the model, right? Prediction and the ground truth. Then in the loss calculation step, the second step, you find a difference between these two in a broad way. But what you actually do here is, in loss calculation step, your prediction doesn't matter. Your prediction of $99, for example, is doesn't matter here. Okay, what matters is your probability of your $89, the ground truth. So when you're, suppose your ground truth is $89 and your model throws out a probability distribution, in loss calculation step, you figure out what probability your model assigned to the ground truth of that item, right? And that number that you get, suppose zero point 0.3 was the probability highest one for $99, which your model predicted fine. Okay. But $89 is the ground truth. Suppose your model gave it like 0.2 as the probability. Okay. And what you do is you take a negative log of the probability 0.2 and you get a number. That is your loss. That is your cross entropy loss calculation. Okay. Uh, now, negative log of a small number is a big number. So if your model gave less probability to your ground truth, then your loss number will be higher, right? And vice versa. And log of 1 is 0. So if your model gave, like, the model predicted only like one outcome, and that is like 100% probability of 1, then your loss will be 0. That is an ideal thingy which we don't expect to have. Okay, that will be overfitting. There could be a case for overfitting as well. But the whole point of loss calculation is figuring out the negative log of the probability which your model assigned to the ground truth, right? And the whole purpose of your training or your fine tuning is to bring down that loss, right? Third step is your backward pass, or back propagation, as we call it also. In that step, what you do is, now you find the gradients, in the sense you figure out which all parameters you need to tweak, by what magnitude, and in what direction, to minimize the loss. That maths, that calculation you do in the back propagation step, right? Now, I have a I have a line of history from for this step, wherein oh, before late 1980s, the math that was used to calculate the backward pass, the gradients, the delta for the parameters was very complex. Okay. And in 1970s, there was a paper on back propagation. Okay. And in late 1980s, this guy, Geoffrey Hinton, or Jeff Hinton, the godfather of AI, he picked up this backpropagation paper and he implemented that to find the gradients. Okay. And the math became pretty fast and simple after that. So that backpropagation technique is being used here to find the gradients. Okay. That is what parameters you need to tweak by what magnitude and in what direction. And the last step is the optimization where you actually apply those gradients on the parameters. Okay. And then you run the next training example. And then you figure out the loss again to see if the loss went up or down. Again, you find the gradients. Again, you apply those gradients and move to the next training example. So keep on iterating on that. That is a whole path of fine tuning, right? Um, okay. What else on this? I'm not okay. Now, if you use gradients to minimize the loss, right? I think that is termed as gradient-based optimization, right? Uh, okay. I'm just trying to recall what all I can add here. I don't have my notes. I don't have any reference from, so I'm just thinking. So till now, anything that you want to guys want to correct or add, and have any questions on, we can delve into those tangents.
Just to add one point to little more clarify, we are in the startings we are going with random weights, and in the gradients, no, the back propagations what we are doing there, we are adjusting the weight, like creating the new weights, and with the new weight again we are doing the forward propagations. So the purpose of back propagation is to create the new weights, because for the every features we have a weight, correct now. So those weights we are adjusting in the back propagations by with the help of the gradient descents. Nag Vishnu, correct now?
That's correct, Dhananjay. Yes.
So that's where like multiple iteration epochs that you do, right?
Yes.
Mhm.
So keep updating the
Okay.
new weights, and based once we can see like with this particular weights, now our output is acceptable acceptable form. So that weight we preserve, and we can say yes. Now once the new data is come, using this weight we do the predictions. So the whole purpose is to come with the weights of the each the in every parameters like the features, because every bias and all call we as a parameter, no?
So this, when you talk about features, when you talk about parameters, when you talk about weights, you're referring to the same thing, right?
No, it's not the same thing.
No,
Features.
Okay.
everything is different.
No,
So
features
features
have
is
weights.
in range
Okay, I
and
can
yeah,
recall.
weights are nothing but like when we will be adding more like uh, more what I can say for
What
certain
the
layer if
importance we should give to this feature,
yeah
correct, Nana?
importance, that's correct. If we are giving more importance, then we are adding more weight to that particular layer. So that's a prioritizing from other layers to the other layer. So that is uh, one is you were talking about the features also, right? So feature is nothing but the list of attributes which are basically contributing to your model output. Okay,
Yes.
like
Yeah, I overspoke there. I actually meant, sorry,
mm,
actually meant the difference between your mm, parameters and weights, right? Are they the same? Are they the
okay.
same name for the same thing?
No, parameter is different. Parameter can be like the alpha values that I'm not sure like if you're familiar with it.
No,
So
no.
there is like different
See,
values.
every
Parameter.
feature you are doing multiply with the weights, na? Those one units is the parameter. Again, like how many we are doing.
Oh, okay.
Correct,
So features
Nagda?
into weights is the parameter. Okay, okay.
Like the base also could be like the bias also is the one parameter. So you can see there is a formula to calculate the parameters. There is taking the how many features parameters, and is calculate the parameters. How many parameters we have.
So is it safe to say that feature into weight is a parameter?
Teacher? No. In
I think
DNN,
No, don't
Features you
confuse
cannot
like that.
say.
So maybe
Yeah.
I can give you an example. For example, if you're doing a gradient descent, how quickly you want to do that descent, right? For example, you can take 10 laps, 10 jumps initially, then slow down,
Learning rate, right? Okay.
right? So that is the parameter.
No, that's hyperparameter now.
Correct.
Those
So
are
what
hyperparameters.
Right, hyperparameters.
correct. That's what I'm referring to.
Yeah.
Right.
Okay.
So
Okay,
that is
very
I
like
simple
tunable,
terms.
you
Like,
can say, right? So how quickly you
right.
want to go to the maxima or minima, right? That parameter, like you can say like 100 iteration you will take to go there, or sometimes 10 iteration, but you might miss the maxima minima there, right? So those are the
Yeah.
actually what is the
I
Learning
think
ideal?
rate,
I
Nag.
Yeah.
learning rate.
So,
Yeah, I
That is
think
learning.
I understand what Nag is saying, but my question is a bit different there. So hyperparameters, I'm aware. So just to give context to Arun as well. So hyperparameters are the ones that are not the model parameters. Those are the training parameters, right? Like epochs, like
that's
learning
right.
rate.
Right.
And when I talk about fine tuning, I talk not about the hyperparameters. I talk about the parameters of the model which we need to apply the gradients on so that the loss is minimal,
Right.
right? So what I'm asking is, when I talk about I need to apply the gradients. I need to do the gradient based optimization of the model's parameters. And when I talk about those parameters, what am I talking about? Am I talking about the feature into weight, what is called as a parameter, and we tweak the weights of the features, which is the parameter in a whole. Do I mean that when I'm tweaking the parameters?
No, it's a weights. Weights and biases are the parameters. Like if you say llama 7 billion or 70 billion parameters,
So those are weights. Okay.
that's the weights actually.
So if
And
I say
features.
llama,
Hmm.
yeah. No, so just to clarify, okay. So when I say Llama 3.23 billion parameter model, by
Yeah.
that I mean 3 billion features and hence 3
Not
billion weights of the
features.
model. And
Not features. It's weights.
but okay, weights. Okay, so you showed a formula on a slide earlier, Pawan, where you said, okay, we do feature into weight, and aggregate all of them, and then add bias to it, and that is some great some you summarization you said, right? Some value is there. So you do feature into weight and then add the bias and then aggregate all that thing into a value, something you called it.
Feature
So,
that actually in the traditional ML algorithm you can consider that. Okay, suppose you are having the linear
oh,
regression, you can consider that. But here in the neural networks, what happens is that we are not giving any features. Features will be extracted by the neural networks itself, and we will not know what features it has extracted. Okay, like for
understood.
example, if you feed an image into the deep neural networks, it will extract the edges, it will extract the like face, nose, all those things, features, right? It will
Understood.
automatically
Understood.
extract. Yeah, yeah.
Understood. Okay. Yeah. So, okay. So features are the ones that has an impact on the output, that has relevance to the output, that has correlations amongst themselves as well. And we will not be able to see, in case of deep neural networks, what features the DNN figured out. In machine learning, we actually set the features, I think. And in case of when I talk about Llama 3.23 billion model, when 3 billion are actually the weights of the model. Okay. And we tweak those weights to actually fine tune the model to behave certain way. Is that right to
Yeah.
say? Okay. All right. All right. Yeah, so fine, that is fine. In my example, the data set which I used was from Amazon, for example, and I had the ground truth value for that data. Okay, that is what I used to calculate the loss as well and fine tune the model accordingly. That was a supervised data, that was a labeled data. Okay, now coming back to your question which you asked, Pawan, I didn't get clarity on the answer to that question which you asked initially. Like if you don't have the supervised or labeled data, right, you don't know what is the ground truth for your data, right, then how will you use the do you actually use the unsupervised data for fine tuning as well, or training as well? I
Yeah,
mean,
I can answer this.
Yeah.
yeah.
So, Yeah. So basically, you are saying your question is like, can we use unsupervised data to fine-tune our model? Is that the question? I mean,
Yeah, I mean, I know we can use, but how do you use it?
Hmm.
What I really wanted to ask. So yeah.
Yeah, we can use, if you like example, we can use RAG here. Okay. If you have a certain data, fine-tuning is nothing but already a model which you are implementation. Like we'll be doing the chunking, then we'll be doing storing, we'll be
Yes,
doing
yes,
the storing in the vector DB. Okay. Then from vector
yes.
DB, there will be clustering happening or similarity will be there. So whenever a user inputs it, okay, I want this detail. So majority of the detail will be coming it from model. Okay. That is said.
Mm.
Then RAG will filter out, or model will take reference of the RAG document to modify their output whenever they will be providing it to you, Vinal. That's what exactly
Okay.
we can handle it. So this is one of the ways we can fine tune our model to align more on our use case.
Okay. All
Oh,
right. See, I have, I have a doubt
mhm,
here. Okay, in the sense,
mhm. Yeah.
uh, you, what from what I am understanding. Sorry, my understanding is very limited here. So please,
No worries.
pardon
Yeah,
me
yeah, no
for.
worries.
Okay, so here you are using model in the inference way to get the better results by using RAG
Mhm,
along with your model to get better results. Okay, but I'm
mhm,
talking about training. I'm talking about fine-tuning your model on the data. When I'm talking about doing the loss calculation, backward propagation steps, and all those
mhm,
like all things like that. Okay. So
mhm,
if you do not have labeled data, so to speak, like I had in my example where I knew the ground truth, I knew the price is at $89,
mhm.
and I let the model predict the value, and then I found the loss accordingly, and then I went ahead with the fixing the gradients and all, applying the gradients on the
Okay.
weights and fixing the weights and all. What my question is,
Mm,
if you
mm,
do not have the labeled data like I had in my example of price predictor, okay,
mm, mm,
if
mm,
you only
mm.
have unlabeled data, right? Can you use the data for uh, training the model or fine tuning the model or not? I somehow know we can. I mean I know we can do use the unlabeled data and
Mhm,
fine tune the model or training the model on that. But since the data is not labeled, how do you find the
mhm.
ground truth? How do you do the loss calculation? Is what I'm confused about. How do
Okay,
you do that?
okay.
What techniques you apply on?
Hmm.
Can I add something? Just one liner.
Yeah,
I
yeah,
think
Dhananjay,
the
go ahead.
way Vishnu explained, na, see, for the different data types, you have different algorithms. As he explains, one of them is the k-means. The way you calculate the center, there also you calculate your loss and all. Algorithms approach is the different. Another is the SBM. Okay, there's
Okay.
you like if you see the SBM, what was the
S-
what was the full form, Vishnu?
I
I
know
just forgot.
Okay.
SGD, stochastic
No,
gradient descent,
SBM.
is what I know.
No,
But
not a
SBM,
specified distance. Like the
Rag?
unlabeled data, the data is not labeled, then you need to segregate as a clustering, different type of clustering.
Ah, A
And
means
there
clustering. Yeah.
also k-means clustering and the SBMs. Vector,
Hmm,
the one is the vector. Now we create two vector between this and then we segregate the data and we
hmm,
try
hmm,
to
hmm,
get the distance between these two data. Where are the maximums? Let me recall this ones. So there is a different algorithms you can say, Binals, to handle unsupervised learning. It's not like only we always needs there also we assume some things and then we start like if you see the k-means how it's working, we assume some in the starting, okay, this is the label, and then we start correcting our label output also just by create
hmm.
finding the distance and all. So just go through this all the different what to say algorithms which handle the unsupervised data.
Okay, I'll just
okay,
add to that. Okay,
Mm.
this clustering, that part, right? I mean, correct me if I'm wrong. That comes in the traditional machine learning. This one, right? In
Hmm.
in deep learning, as far as I understand, I guess that won't happen. Um, I mean.
okay.
At least I don't know. I can't think of Okay, I may be wrong. But
I
yeah,
think,
at this moment, yeah,
in these generative AI models like auto encoders, diffusion models, those all deals completely on supervised learning data.
correct. Yes.
And those algorithms use in our deep learning models to create the new data, generate the new data, na, based on the models, and those complete
Right.
data also the what to say is the like this complete this all completely working on supervised learning data only.
Supervised.
All these generative, like auto encoders, diffusion model,
Correct.
BAE models,
Yeah.
which alls.
Right. Okay, I think I'll clarify.
Yeah, yeah.
Okay. So my question was, I think, was wrong. Okay, kind of. It was not fully correct. So what happens is that you can do the unsupervised training on the neural networks, but that is like you do the pre-training. Only in the pre-training you usually do that unsupervised or unlabeled data training. Okay, wherein still the label will be there. The label will be taken as the next word. Okay, by the model itself. That's what I understand. Okay, I put the screenshot of the chat GPT or that Gemini in that. You'll, if you see, you will know that. Okay, so that's how the training is done using the unlabeled data. But for fine tuning, okay, that is done for the pre-training unlabeled data. For fine tuning, once the model is there, you usually do not do the unlabeled fine tuning. You will usually do the fine tuning with the labeled data. I think
Yeah.
that we can keep it as a simple. There may be some possibility of you still using unlabeled data and all, but for simply to keep it simple, we will not fine tune with the unlabeled data. We'll always do it with like Dhananjay said, right? It's always with the labeled data.
Hmm.
Okay.
Got it, man. Understood. I got the point. Yes. So if we have to use fine tuning, we should use labeled data. That is the whole point of fine tuning. But if you're building a model from scratch, you're doing the training, not the fine tuning, then you can use the unstructured data as well to learn for the model to learn the new data, learn new facts, and all those things. Okay. Right? That is the whole point.
Yeah, correct.
I think that is fine. That is fine. Okay. Thanks for clarifying that. Okay. That was that was a good question which you asked initially, and that triggered my chain of thought for types of data, and that clarified this thing here. So that's a good productive question you asked. All right. Fine. So forward pass is pretty simple. Loss calculation is pretty simple. Now, in the backward pass step, right? What I mentioned about the back propagation and all, right? So in backward pass, like back propagation is technique we use in backward pass, right? And that is what my understanding is. So are there any other techniques that we use in backward pass?
Very bad at back propagation.
Okay.
I honestly did not get your answer also, but I'll let others answer if they want.
I can
So
repeat my
so
Period
you
question.
are asking
gradient, he
about
said.
the techniques.
Yeah, my question here is like in backward pass, back propagation is a technique we follow to calculate the gradients, right, which we apply in the
Hmm.
optimization step. So back propagation is a technique which we